Welcome to Unit 13, Section 1, Numerical Integration. Now, before we get into it, let's talk about why we need this. And up to this point, we've had a few different techniques on how we can integrate functions analytically, and we use things like substitution to integrate functions that are a little more difficult, and we use some trig identities to simplify things so that we can get functions into a form that we can integrate. Well, what if there's a function that we can't integrate, such as something like the integral of cosine x squared dx? There's really no technique, there's no u substitution that we can use or anything to integrate this. This is a non-integrable function, and so we have to resort to approximation techniques. And so that's what numerical integration is. We're going to revisit some more approximations, and we're going to look at approximations that are as close as possible to what the real answer is without actually being able to find things analytically. Now, I'm going to preface this video a little bit. The functions that we're going to deal with in this video and the functions I'm going to assign you are going to primarily be functions that can be integrated. So don't think that why are we learning this new technique when I can just use my old techniques of integration. The functions that you see with this video will be ones that you can integrate, but we're using those to learn the technique of numerical integration and to check to make sure we're doing the right thing. Then we're going to apply this to functions that cannot be integrated, and that is the real use and the real meaning of why we use numerical integration. So let's start off with, if we're going to use approximations, we have to bring in this idea of error. And so suppose C is a computed numerical solution to a problem that has an exact solution of x. Whether we know x or whether we don't know x, doesn't matter. And there are two common measures of error that we're going to use to describe C as an approximation of x. There's the absolute error, and the absolute error is simply just the absolute value of the difference between C and x. So whatever C is, subtract x from it, take the absolute value. That gives us the absolute error. So how far off are we? The relative error is typically going to be given as a percent. Okay, so we want to give the relative error as a percent because we take the absolute error and we divide by the exact solution. And this at times will give us a more meaningful error. And it depends on the situation. Sometimes an absolute error is more meaningful than the relative error. So let's look at an example. Let's say, think back to the ancient Greeks. And the ancient Greeks, when they would talk about pi, now we know pi is equal to, and even this is an approximate, it's 3.1415926, so on and so forth. Okay, so pi has an infinite number of digits. Well, the Greeks, what they would use is they would use 22/7 to approximate pi. They would say 22/7 is close enough to pi, and that's what we're going to use. So pi is an exact number, and that's our x. So x is pi, and the approximation here, C, is equal to 22/7. So if we want to find the absolute error, that would be the absolute value of 22/7 minus pi, which gives us about 1.3 times 10 to the negative third. So the difference between 22/7 and pi is absolutely 1.3 times 10 to the negative third. So we're talking about 1/1000th or 13/10,000ths off. Now let's give that some perspective. Let's talk about how much of pi is that. So how much of pi are we missing? What percentage of pi is C missing out on? So we take that and we divide by the value of pi here, and we find that we get 4 times 10 to the negative fourth, or what we get is 0.04%. So really, this is a small value. So we could evaluate this to say that, hey, we're less than 0.1% off by using 22/7 as our value of pi. So depending on what calculations or what tabulations you're doing, you can simply use that as your approximation because it's pretty darn close. Okay, now when we were dealing with functions before, and before we even talked about integrating, let's say we have a function that looks something like this. And we want to find the area under the curve from, let's say, from this point A to this point B. Okay, so we want to find this area. Now, when we first talked about this, we would divide into sub-intervals. And when we divide it into sub-intervals, we use the Riemann sums. Okay, we use the left Riemann sum, we use right Riemann sum, and then we use the midpoint Riemann sum. And I'm going to bring back that midpoint Riemann sum to talk about that slightly here. In that, when we have this function, any function that we'll call f of x, all right, and we want to find the area under the curve, or integrate, essentially what we're doing here is we're integrating from a to b of f of x dx, but let's say the function is not able to be integrated. It's not a nice function if we have the function rule, but we can still find the area under the curve by using these approximation techniques. And those techniques depend on the number of subintervals. So let's define some things here. We're going to call this x0, and then this would be x1, and this would be x2, and this would be x3, this would be x4, and this would be x5. All right, how many subintervals do we have here? We have 1, 2, 3, 4, 5. That's our number right there, k. And we can say that this integral from a to b is approximately the midpoint sum here, m sub n. And so let's recall what that is. If we recall back to our midpoint formula here, what we're doing is we're actually finding the area of these individual rectangles here. And we're not going to pick the left point to define the height. We're not going to pick the right point to define the height. We're going to pick the midpoint. Okay, so some point in here, that's going to define our height. And so to find that midpoint, we have to add these two x values together and divide by 2 and evaluate our function there. So that's going to give us this point up here. And we're going to do the same for that. Find the midpoint there, find the midpoint there, find the midpoint there, find the midpoint there. And we're going to evaluate our function at all those midpoints. So that's what this is saying right here. This is evaluate the function at those midpoints, and then we're going to multiply by delta x. Now, let's remember, what is delta x? That's our interval, the width of our interval divided by the number of subintervals. So delta x gets smaller as n gets bigger. Okay, right here we have our situation, we only have 5 subintervals, so this would be whatever b is minus a divided by 5, that would be our delta x. And x sub k is defined as a, our starting point, plus k times delta x. So how many delta x's are we away from our starting point? Okay, so let's use a function that we know the end result to test this out. Okay, so we know that the integral, or we can at least find the integral of, let's say, x squared dx, and let's go from 2 to 4. Now, we know that this exact value here, let's go ahead and find the exact value using our normal techniques. This would just equal x cubed over 3 evaluated from 2 to 4, and so that would give us 4 cubed divided by 3, so that's 64 divided by 3 minus 2 cubed divided by 3, that would be 8 over 3, and so that would give us 56 thirds. Okay, so we know what the exact answer is. We know it's 56 thirds. Now let's use our midpoint approximation to see how accurate is our midpoint. What type of error do we have? And let's do it for 2 situations. Let's look at when n is equal to 4 and when n is equal to 8. So let's first start with n equal to 4. Well, if n is equal to 4, we know that a is equal to 2, b is equal to 4, so that means delta x is equal to 2 over 4, or in other words, it's 1/2. Okay, so delta x is 1/2, and so what we want is we want to find the sum from k equal to 1 to n, in this case is 4, of f of xk minus 1 plus xk over 2, and we want to multiply by delta x. So what this is we need to check all the midpoints. So we need to know, and it might help to make a list of, well, what's x0, what's x1, what's x2, what's x3, what's x4. Well, we know x0 is going to be 2, we know x4 is going to be 4, and our delta x is going to be 1/2, so this is going to be 2.5, So we can go ahead and write a decimal, 2.5, this would make that 3, this would make that 3.5. Now, if you recall, if we wanted to find the left Riemann sum, we would use these four. If we wanted to find the right Riemann sum, we would use these four. Now, what we're trying to find here is the midpoint, so we need the midpoint for each of these. So the midpoint between 2 and 2.5 is 2 1/4, 2.25. The midpoint between 2.5 and 3 is 2.75, and so forth. And that's what we're going to use here. So we're going to take our delta x 1/2, multiply by each of these midpoints squared. Why are we squaring them? Because that's what our function is. Our function is x squared. So this is going to be 1/2 times 2.25 squared plus 2.75 squared plus 3.25 squared plus 3.75 squared. And when we do all that, we get a result of 16.625, or excuse me, 18.625. So let's compare that with our exact result of the 56 thirds. And if we write 56 thirds as a decimal, we get 18. This is approximately 18.667. It's 6 repeating. So we look at, well, that's close, but how close are we? Let's find our error. Let's find our absolute and our relative error. So our approximation that we had here, our approximation C, was our 18.625. Well, we know the exact answer is 18.6 repeating. Okay, so let's find the absolute error. Well, the absolute error is equal to the absolute value of the 18.625 minus the 18.6 repeating, which is approximately, and I should use approximate here, approximately 0.042. So this is our absolute error. Now, if we want to find our relative error, we need to divide that by our 56 thirds, or our 18.6 repeating. So we take that, we divide those two, and we find that we have a relative error of about 0.223%. Okay, so we're less than 1%, about 0.2%, a little more. All right, now what I want you to do is I want you to try to repeat this process, but do it for n equals 8. And think about what you would expect. Would you expect this to be more accurate or less accurate than when n equals 4? So pause the video, try that, and then press play on the video to see what your results are. So whether you tried this on your own or if you just continued watching to see what the results are, when you find m of 8, you get that to equal an 18.65625. So that's a little bigger than our last one, and in fact it's a little closer to our actual answer of 56 thirds. And so if you find a relative error, the relative error here is going to equal approximately 0.0558%. Okay, so we're down to 0.05%, which is more accurate. And as you would expect, the more subintervals you have, the more accurate your approximation is. And once again, we use this to illustrate how to use the approximation, how to find the error. We know how to integrate x squared. The purpose of these techniques are not going to be to integrate x squared, but we're going to use these techniques on simple functions first to get the hang of it, and then we're going to apply it to functions where it's really useful. So I'd like you to try a couple of these before you come into class tomorrow, and I want you to turn to page 610. Now we're going to use these problems on page 610, and we're going to adjust the direction slightly. On page 610, I want you to look at numbers 1, 3, and 5. And I want you to do like the directions say in finding the midpoint approximation, but we're just going to use the midpoint approximation. They're going to ask you to do trapezoid and Simpson's rule. Don't worry about that. We're going to do that later. I want you to do the midpoint approximation, and then find both errors. Find the errors, and I'm talking about absolute and the relative. So find both absolute and relative errors for all three of these functions. All right.